Start recording. All right. John, you can see the screen, and we need to bring up the notes. So, Blackboard has decided that they need to use their space for other things. Okay. Here we go. Table of contents. Here we go. And linear 4.1. Okay. Now, of course, to begin this study of vector spaces, we're going to start with our familiar vector spaces, and that's Rn. Okay, and I'm hoping that this picture is extremely familiar, and in this case, we are talking about the vector spaces from calculus. So, a vector can be thought of as an arrow, right? If its base is at the origin, its tip has coordinates in which the first coordinate is the length left and right, where left is positive and right is negative along the x-axis. And the second coordinate is its length parallel to the y-axis, where up is positive and down is negative. And this always forms a right triangle because it's this kind of coordinate system. And from this right triangle, we can compute the length or magnitude of the vector or the norm of a vector. Okay, so these three things all mean the same thing. Norm of a vector, magnitude of a vector, length of a vector. And in this case, in Rn, the magnitude or norm of the vector is the square root of y1 squared plus y2 squared. You'll notice that we use a single bar around the vector to indicate its norm. However, we will not always do that. Sometimes we use double bars. Double bars and single bars for a vector mean the same thing. They mean its magnitude, its length, or its norm. The thing to keep in mind is in this course, we're going to go from the vector spaces Rn, starting with R2 and R3, which we are very familiar with, okay, and move into more abstract vector spaces. So there is vocabulary that we use for abstract vector spaces, but they are also true for Rn and R2 and R3, okay? But R2 and R3 have this other older vocabulary. So norm is the new vocabulary that we'll use for all vector spaces. But magnitude and length is the old vocabulary from R2 and R3 that is also used for Rn. And we'll explain in Chapter 5 the difference between some of these norms and lengths and magnitudes. And a vector has a direction. And in R2 and Rn, that direction is an angle with an axis. In the case of the plane, we have a length and an angle. Notice we have two pieces of information. Those two pieces of information, length and angle, put us in the same spot from the origin for the tip of the vector as the coordinates y1 and y2 would give us.
Are we talking about polar coordinates? Is that what
Yes, we're talking about polar coordinates. And the thing to notice is that in R2, it always requires two pieces of information to tell you about the vector. Okay, this is a very familiar picture, yes? Okay. The thing that may not be immediately aware, you may not have thought of before, but certainly if you think back to your physics first semester physics class, you will realize this is true, is that all of these vectors are vector x. Knowing the direction and the magnitude does not tell you where you are. It only tells you what direction you're going and how fast.
That's a question I have for my top three professor. He said that they'll just have to wait to work that out, you know?
Okay.
He said that you'll have to wait to work out. You'll have to wait to learn more specifics on vectors. Wouldn't it always just be head, tail?
I'm sorry?
Wouldn't it just be head, tail to move it to the origin and then we anchor
Just a little louder because you're wearing masks.
But don't we usually anchor them to the origin and therefore that's a useful point?
Let's talk about that. All of these vectors are the same vector. And in fact, you can find its coordinates in the, in I hat and j hat in the Euclidean coordinate system, Rn, simply by subtracting the tail from the tip. Because when you do that, you get y2 minus y1 for the height, and you get x2 minus x1 for the length, which gives you the same right triangle with the same hypotenuse. That'll give you the same angle with the positive x-axis and the same magnitude, square root of the squares of the sum of the squares of the sides of the legs of the triangle. Now, notice one of those vectors has as its tail, its base, the origin. When the vector is located in the origin of your coordinate system, we say that the vector is in standard position. And that's when the coordinates of the vector line up exactly with where the tip sits. Okay? Any other place the vector may be located, to find its coordinates, you have to subtract the tail's coordinates from the tip's coordinates. And then that will give you its coordinates in standard position. But all of these vectors are identical. They are all labeled x because they're the same vector. Knowing the vector's direction and magnitude only tells you what direction you're headed and how hard, how much force you're applying. It does not tell you where you are. The location of the base of the vector tells you where you are, and that's a point with round brackets, right? Remember, the vector itself, we always list the standard coordinates, and we use angle brackets, or we use the column vector with square brackets. Although you can use round brackets for a column vector, that's okay.
Or we use unit vectors?
What?
Or we use them as the linear combination of unit vectors?
Or we can write them as the linear. But notice that those very same scalars that scale the unit vector, the I hat, j hat, and k hat, turn out to be the coordinates in standard position.
Right.
And that's the observations that we want to make. Okay, so here we are. This is what we just talked about. We can write a vector as a column vector. We can use angle brackets, which mean I'm really a column vector. Why do we have the angle bracket notation? Because the Calculus 3 book would be 3 times as thick if we had so few lines per page that we put column vectors everywhere. So we started typesetting vectors like 300 years ago as row vectors with angle brackets so that we didn't have to waste space when we were typesetting.
Oh, so those just indicate that is actually a transposed matrix and we're writing it wrong.
Transpose isn't really correct because the angle brackets are telling us I'm really a column vector. Not that you should transpose it. And of course, as we noticed, we can write it as a linear combination of our basis vectors I hat and j hat. Now, we are going to get away from calling our basis vectors I hat, j hat, and k hat because we want to be able to talk about Rn where n is much bigger than 3. And we run out of letters really fast. So instead, we're going to call them elementary basis vectors E1, E2, E3, E4, up to En. Okay? So E1 with the boldface E and I hat mean the same thing. Boldface E2 and j hat mean the same thing. And boldface E sub 3 with the vector boldface and k hat mean the same thing. Yeah.
I have a question about notations for column vectors and row vectors.
Yeah.
So for the column vector, we're using the angle bracket, but for the row vector, I think
We would use square brackets.
Okay, square brackets.
Okay, so let me point something out. Although you have used them in the past, there is no such thing as a row vector. It is a 1 by n matrix. It is a linear transformation. It is the dual of a column vector, of a vector. Did you watch the video on dot products yet? I haven't assigned it. He talks about the dual. Okay. There really is no such thing as a row vector. We say row vector all the time, and we mean the transpose of a vector, right? But vectors are column vectors. Its dual is a 1 by n matrix, and the matrices represent linear transformations, right?
Right.
And it's a linear transformation from Rn to R1. And in fact, we're going to learn chapter 5, it's the dot product linear transformation. Because isn't U dot V, V transpose times U, using matrix multiplication? We'll talk about that in chapter 5. We don't have to talk about that yet, okay?
That's cool.
Now, the physicist's perspective is one we're really familiar with, where it's an arrow in space. And the computer science perspective is that it's a list of numbers, and that we can do all of our linear algebra with lists of numbers and with arrows in space. The problem is, we would like to take this very familiar Rn, especially R2 and R3, and generalize this to other vector spaces in which drawing the vector is impossible, and writing down the vector is impossible because it has an infinite number of coordinates.
What?
Oh, yes. In fact, these are the reason you're taking the class. You're not taking this class for R2 or R3 or even Rn. You're taking the class for these abstract vector spaces. And there's a big reason for that. In our century, all of our technology, especially this one, uses the fact that we can take a very complicated physics or engineering problem and write it using a domain that's a vector space, a range that's a vector space, and a linear transformation. If we can do that, then the computing devices that we've created, which love doing vector operations, will do all of our arithmetic for us. And this is necessary. Even, has anyone used a search engine before?
Yeah.
Okay, how many hits do you typically get?
10,000.
Millions and millions. It only shows you the first few, right? Page ranking is a huge problem that involves, how many web pages do you think are out there?
Millions?
I don't know if we've hit B yet, but we're over M, millions of web pages, and yet we're able to page rank all of them. I mean, even if we only had one web page for every person, we would be in the billions, but I don't think we're there yet.
1.7 billion.
Oh, we are in Bs. Okay. Well, okay, so I will use the I'm old thing and just didn't realize we had managed to cross the $1 billion mark. Okay. So, notice the use of the double bars. Double bar, single bar means the same thing. But we reserve the double bars usually for these abstract vector spaces when we're talking about their norm. But norm is a word that applies just as easily to Rn, where we usually use single bars, and norm in Rn means magnitude or length, and is the square root of the sum of the squares. And in Rn, even if n is 57, you can find angles, and the angle between two vectors in a 57-dimensional vector space will still be the dot product of the two vectors divided by their lengths. And that's because even in three-dimensional space, I can draw a right triangle, even if it's not in a plane that's vertical, horizontal, right? Or this way vertical. And I still have length squared plus length squared equal hypotenuse squared, and I still have the cosine of the included angle is equal to the side adjacent over the hypotenuse. So this still works, because remember x dot y is the length of x times the length of y times the cosine of the angle between them. That's the actual definition of dot product, which we'll talk about in chapter 5. Scalar multiplication still works. And I'm hoping all of this is, wait a minute, why are we reviewing all this? Didn't we talk about this in chapter 1? Well, I want it to be very fresh in your mind in just a minute. Okay, addition still works. And in addition, we can use the physicist's perspective or the list of numbers perspective. But we still end up adding, right, the corresponding coordinates. Addition is commutative, which you can see from the list of numbers perspective here, or you can draw the parallelogram and see that vector addition is commutative. All right, so there are exercises sprinkled throughout here. I like these better than the examples that are in the textbook because you get to sit, yeah, I'm telling you, sit down and calculate this and then check to make sure you have the right answer. Okay, here are the properties of vector addition and scalar multiplication on the plane. And we might as well say in three-dimensional space too. The two vector spaces we are very familiar with. And that is the sum of two vectors in the plane or in three-dimensional space is a vector in the plane or three-dimensional space, respectively. That addition is commutative. Notice that unlike the textbook, I did not list the fancy terms. That's because they're not necessary. I know this class has enough vocabulary already. You don't need to be an algebraist and memorize the fancy definitions for all of these properties, words, vocabulary terms for each of these properties. You just have to be able to use them and recognize them, okay? So u plus v equals v plus u. In other words, it's commutative. That if I have three vectors to add up, I can add up the first two and add it to the third, or I can add the first to the sum of the second two. It's associative. There is a zero element somewhere in the vector space. There is a vector that I can add to any other vector, and I get the vector I added the zero to back.
The zero vector?
The zero vector. It is, even in an abstract vector space, it is always denoted with a bold zero, or zero with the bar over it if I'm using my notes. There is always an additive inverse. There's always a vector for every other vector that I can add to it to get the zero vector. Of course, the zero vector is its own additive inverse. And it is -1 times the vector, right? These things should always be true. All right, now, the constant times the vector is another vector.
Yeah.
If I, multiplying by a constant, distributes over vector addition. Scalar multiplication of a sum distributes over scalar vector multiplication. And scalar multiplication is associative. C times D times the vector is also C times D times the vector. And finally, if I multiply a vector by the scalar 1, then it doesn't change the vector at all. It's the same vector. And these 10 properties are things that we've been using for the first 3 chapters every day.
Yeah.
Okay. How can we prove them? Well, here's an example. Remember, we went through proofs like this. And the book gave 2 examples, and I gave a different 2 examples. Okay? He didn't prove all 10, he just proved 2 of them and said, do the other 8. I proved a different 2, so now you're down to 6. Okay? All right. In R3, everything works the same. You should verify that you can compute 2u plus v, 5v, and 3u minus 4v correctly, and check the answer to make sure that you get the right answer. I am very confident that everyone will get the right answer, okay? At least I really hope that we all brought this knowledge with us. Okay. Now, what about Rn? I want you to notice it's the exact set of 10 rules. All of these properties work even if we have a 128 by right dimensional vector. But the thing is, how do we prove them? Okay, so here's a way. This is the way that was used when I was an undergraduate, and it's in your textbook, the way that I showed number 2. Again, the author chose to prove 2 of the 10 properties, and I choose a different 2. All right? And he's using the list of numbers and angle brackets in order to keep the amount of writing down so that you don't fill your page with writing for just one of these. Right? Does this make sense? You add 2 vectors by adding the corresponding elements, but each of those is in sums of real numbers, which is commutes, because we learned that in K through 12. And then we separate it back out into vectors, and now we've just proved that u plus v equals v plus u.
Okay.
But I showed you an easier way to do that.
Oh yeah, UI, VI, because,
Yeah.
because that UI is that list.
That's right. Notice there's only one subscript because I'm lazy and I'm a mathematician. I didn't want to write one I and one, every single time, because all those ones, every one of those, if I used 2 subscripts, would be a 1I. So that was a waste of time. Or no, they wouldn't. They'd be 1, 2, 3, 4, 5, 7, 8, 9, 10. It'd be J1, I1 and I2 and I, yeah. So anyway, there are certain properties that are not on that list, but they can be easily proven by the 10 properties on that list. One of them is that if v plus u equals v, then u must be the 0 vector. And we're going to prove that in a second. That if v plus u equals 0, then v must be the negative of u. They must be additive inverses. That 0 times any vector is the 0 vector. That the constant multiple of the 0 vector is always the 0 vector. And that if a constant times a vector is the 0 vector, then either the constant was 0 or the vector was the 0 vector. Do these properties make sense to you? And that the additive inverse of the additive inverse of a vector is is itself.
For example.
Okay, well, let's look at how we might prove one of those. Notice I only use the 10 properties from Theorem 4.2. Theorem 4.2 means the first property in Theorem 4.2, and Theorem 4.2.4 means the fourth property in Theorem 4.2. Remember, we have Theorem 4.2 up here. So we can actually prove all of these 6 properties, and here's an example of how to do it. And by the way, the author proves one, and I proved a different one. Okay? How are we doing so far? I'm trying to get you into abstract vector spaces. And that means when we talk about abstract vector spaces, we're going to be doing a lot of homework problems like this, where there are no numbers in sight. Right? Because, for one thing, if it's an infinite dimensional vector space, listing all the numbers would be a complete waste of time, since none of us would ever finish before we passed on. Right?
So,
Or when it's saying,
like one and say,
Huh?
the sum of all the elements, and then get rid, and
Yeah.
then deal with that, you don't have to deal with that?
That's what we're going to do. Okay. How are we doing? How are we doing at home, John, or remotely? Are you following along?
I'm following.
Okay, good. All right, let's go on to the next page. Vector spaces. Okay. This is the one that gives people the most trouble. And this is a good time, if you have the time at home, to watch, I think starting at, I don't think you have to watch, starting at 20 minutes and 20 seconds, so you don't really have to watch the first 20 minutes. Because he's talking about stuff we already did. Permutations, and transposes. But then he's going to start talking about vector spaces in Rn. And if you have any questions at all about what we've been discussing in class, you can always watch him explain it. He's going to explain exactly the same thing. He's just going to say it a slightly different way. Yeah.
I already watched it. It's a little bit confusing. Like, so he was talking about subspaces in vectors.
I know. We're going to talk about subspaces on Thursday.
Really, just kind of confusing.
Okay. Subspaces are always confusing at first, but we'll get past it.
Isn't the subspace we were just projecting an Rn into a lower dimensional space? Isn't
No.
that how that works?
We haven't, but yes. Okay, so the way our 21st century technology works is these are all infinite dimensional vector spaces, the ones we're really interested in. But we can pick a finite dimensional subspace. Now, they're not all infinite dimensional. For instance, if we're doing graphics on a 4K screen, 4K by 4K is a big matrix, right? 4 times 1024 by 4 times 1024, so 16 times 1024 squared.
20 by 1920.
Yeah. So those are big matrices. But your graphics brusher has no problem with that because they don't have any problem doing the same thing over and over and over and over again in a loop, like multiplying and adding and multiplying and adding. No big deal. We, on the other hand, couldn't solve one 4K by 4K problem in less than, a year and a half? and I don't know about you, but I would have made 57,000 errors by the time I got to the end. Okay.
Can I make MATLAB do it for me?
Yes, you can. You can make GeoGebra do it for you. Now, how many people are already familiar with using MATLAB? John, have you used MATLAB before? I can't see you raise your hand.
I've used Octave, which is close to MATLAB.
Octave is fine. It just doesn't have quite the graphing capability that MATLAB have, which is really unfortunate, but it is open source. Okay, that's good. You don't need MATLAB for this class. I used it before 2011. I always taught MATLAB in this class with the linear algebra, so that you do the homework in MATLAB. But
So the question is, what would make this different than numerical methods then?
because we're going to talk about linear algebra, okay, in particular abstract vector spaces and norms and inner products that are not the ones you're familiar with, okay? All right, so how does the definition of a vector space work? Now, this is not a theorem. It is a definition.
Oh,
It's definition 4.1 because it's the first definition in the chapter. Now, these 10 properties are not theorems you can prove about vectors in Rn. It is the definition of a vector space. Sometimes these are called axioms. Okay? So these aren't properties anymore. They are things that must be true. And if we have any set of things for which addition of two of them gives us another one of them, and if I multiply one of them by a scalar, I get another one of them, and that addition and scalar multiplication has all of these 10 properties as true, then we're going to call it a vector space. So what is a vector? Well, in the mathematician's perspective, a vector is an element of a vector space. Because most of the vector spaces that we're really interested in cannot be realized as an arrow in space. And we can't possibly list all the numbers. Okay? But it's still a vector space. Because if we add two of them together, we get another one of them. And if we multiply one of them by a scalar, we get another one of them. Even if it's the same one. For example, there has to be a zero vector somewhere in this vector space. And if we multiply whatever this thing is by a scalar, we still get the zero vector, right? And this is the part that's tough. This is called abstraction. Yeah.
Does the direction of the zero vector matter?
No, it doesn't have direction. You can think of it as having all possible directions, and you can think of it as having no direction. But yes, the angle, that's a very good observation. The zero vector doesn't have a direction, really.
Well, it's a point. It is effectively a point.
Yeah, it is a very diminutive vector, since the tail and the tip are both the same, right?
So it's a point.
But we're going to find out pretty soon. Let's talk about a different zero vector here in a little bit, okay? Notice I haven't posted the notes for 4.3 yet, but I'll get them posted tonight or tomorrow night, and 3 and 4 for Thursday. But we only need 3 sections a week, so 3. Okay. And 3 is obviously subspaces, right? Okay. Now, we want the same kind of thing to happen. But we need to make sure that in our notes, we do not write 0 and that you assume that I know that you meant a vector. Put a bar over it if you mean the zero vector, or put it in bold. How can you write a bold? Well, okay, I am not a big fan. I always write vectors in my notes with a bar over the top. So that's the zero vector, and this is the zero scalar. And I will always use the same notation for the zero vector, no matter what the vector space is. That's the zero vector. But some people like to pretend they can do stuff in bold, so they double bar it, like this. Like if I A, but you'll see why I don't like it.
Because they are, isn't it because that...
Instead of, right? And physicists, some physicists put the bar underneath, because the bar over the top means complex conjugate, right? But I will never use the bar over the top for complex conjugate.
Then what we do write for complex conjugate?
As you will learn in chapter 5. That's an N, not an M. There are 3 other ways to indicate a complex conjugate of a vector or a scalar. The splat, up where the exponent goes, means complex conjugate. More modern physicists use, and I can't draw it very well, the dagger.
Oh. What?
Now, mathematicians use the dagger for adjoint,
Oh.
but physicists use the dagger for complex conjugate. And that's what the dagger looks like. Don't worry about that whole integral thing. We'll talk about that in chapter 5. But
Does that mean I'll finally know how to deal with with Schrodinger's equation by the end of this class?
No, we're not going to go into curving equations. Physicists also use, we're going to use the dot for dot product, but we're also going to use the angle brackets. But unlike physicists, unlike Dirac, we're not going to use a vertical bar between the two vectors. We use a comma between the two vectors for inner product. Okay.
We're not doing broadcast?
Huh?
We're not doing broadcast?
No. Did I say that already in this class?
No.
Yeah. Yeah, he actually calls the left bracket bra and the right bracket ket for bracket.
Yep.
Yeah, I know. Obviously, even in physics and math, there are dad jokes. Okay. The other one is you put an H up here. Now, these, it means Hermitian. It's for a mathematician's name. And the thing is, these things are also used if we have a vector or a matrix. We can have a vector, and if we write the splat or the dagger, which I won't use because I can't draw the dagger. It doesn't look right when you draw it in your notes. It looks like a plus sign 90% of the time. Or, and this is what I typically do, use the H for Hermitian. And it means transpose and conjugate all the elements of the vector. So it's called the conjugate transpose.
Okay.
And I can do the same thing with the matrix. I can transpose a matrix, which means I can transpose it and compute the conjugate of all the elements of the matrix. So this is another way of writing. Now, this is where H is used and dagger is used the most, which the thing that you're conjugate transposing is a matrix. In quantum mechanics, it could be a matrix or a vector, and the dagger and the H mean conjugate transpose. And there are a lot of situations in mathematics where we use the splat because the bar over the top means it's a vector, not conjugate transpose.
I've seen vectors written with an arrow at the top. Is that normal?
Yes, and that's perfectly acceptable.
That's how we typically learn it.
Right. Well, you see a lot of textbooks that use arrow though over the top. So remember, a vector can have an arrow over the top. It can be underneath if you're a physicist, which means you can put an arrow underneath. I've seen all of these in different textbooks and papers, and they all mean the same thing.
I've never seen people put hat instead.
Oh, we're going to do that.
Where V with the bar over the top. Also.
Sometimes we're going to approximate a vector with another vector that's close to it.
Wait a minute, isn't that just I hat?
Well, that's where I hat, J hat, and K hat come from. It's the hat notation for vectors. Okay, but you can use a hat for vector. And in this class, we're going to use the hat to mean approximation to. So, or, right? Well, things are starting to get abstract. And we're going to run out of letters, and we need notational conventions.
There are so many different notations.
Yes, and that's because linear algebra is only 300 years old. In mathematics, that's kind of young. That's sort of like being 19.
But calculus is 400 years old, and we've managed to come up with mostly consistent.
Exactly. You mean like Leibniz notation
Yes.
versus Newtonian notation?
I thought it was F dot.
What?
For Newton's notation, I thought it was F dot.
No, that means the partial derivative with respect to y and then x.
Or was it big F? That's why.
Huh? No, in Newtonian notation, it's y first and x second because you read it left to right. In Leibniz notation, it's function composition. And you read it right to left.
And that's why I like Leibniz.
Yeah, that's why most people like Leibniz better, because it's function composition, and that's what you're really doing. How do you find the second derivative? You compute the first derivative, and then you take that answer and plug it into the derivative again and get the second derivative. It's function composition. Okay. And We're going to use it in this class. Okay. I didn't want you to create a new page. Oh, you deleted the page I wanted to, oh, no, you didn't. Okay, here we go. All right, so let's look at some abstract vector spaces, and this is the easiest new abstract vector space to look at. How about the set of all n by n matrices? Isn't the sum of two n by n matrices an n by n matrix? And if I multiply an n by n matrix by a scalar, don't I get another n by n matrix?
Yeah.
And didn't we already learn in chapter 1 that all of those 10 properties apply to sums and multiples of n by n matrices? So, the set of all n by n matrices with matrix addition and scalar multiplication is a vector space of n by n matrices. And just like you can't add a two-dimensional vector to a three-dimensional vector, you can't add a 3x4 matrix to a 12x2 matrix, right? They have to be the same size, or it doesn't make any sense. Does this make sense? Are we there?
Yeah.
And matrices represent transformations. So this should be leading you to the idea that there are vector spaces of transformations, or vector spaces of functions. And this is why people start to think, okay, this is the hard chapter, because it's very abstract. But certainly, and notice you're going to really like the notation I taught you, because trying to prove them by writing your matrices at the top of the screen would be a nightmare and take pages and pages of work, which is the way I had to do it when I was an undergraduate. But I like the notation at the bottom of the page much better. Right? I mean, which way do you want to do it? Top of the page or bottom of the page? Okay? So the investment you make to understanding the notation is important. And it's very profitable. Okay? And I would strongly suggest to you that even if it doesn't make sense to you at first, when I recommend that you do a problem a certain way, it's because the investment you make into understanding it may take a little more time at first, but you're going to find out that in the long run it's going to be very profitable, or I wouldn't have shown it to you in the first place. Okay? Yeah.
So I have a question about this notation, and I'm sorry I didn't figure this out earlier, but is it possible to use this notation to represent things having to do with matrix multiplication?
Yeah.
Okay.
It's just harder. Matrix multiplication is hard. That's why I had you watch the 3 blue, 1 brown video.
Yeah, it helped a lot.
Using function composition is much easier. So when you're having to do matrix multiplication, write it as function composition, and you'll find that doing the problems is much easier.
Okay.
Okay, linear combinations of, we have linear combinations of matrices, right? It's a vector space after all. Okay, so what does a matrix represent? It's an algebraic representation of a linear transformation that sends I hat to 3, -1 and j hat to 1, 2. So you ought to be able to draw the parallelogram you get when you apply this linear transformation to every single vector point in the unit square. And it ought to give you a picture of a parallelogram that you can easily draw. Now this is a vector space you may or may not have thought of. After all, if I add two polynomials, don't I get another polynomial? And if I multiply a polynomial by a scalar, don't I get another polynomial? And doesn't addition and multiplication by scalars for polynomials follow all of those 10 rules? And isn't this an infinite dimensional vector space? After all, what is the polynomial with highest degree?
There isn't one.
There isn't one, right. There is no polynomial with highest degree, right? Now, every single polynomial has a finite degree. We're not talking about Taylor series from Calc 2 yet. Every polynomial is finite degree, so it's represented by a finite list of numbers. But if I have a polynomial of degree 12, I have 12 numbers and then lots and lots of zeros, right? In fact, an infinite number of zeros. And if I have a polynomial of degree 4, I have 4 numbers and then an infinite number of zeros. So I can't represent this vector space using a column vector because it would take, an infinite number of zeros. Or all of the vectors would have different lengths, which is not really allowed, right? Okay, so what do? We write it the old way, like this.
Well, what's the difference, really?
We're getting there.
You just replace P with Q, right?
So for example, we're going to assume that m equals n. Because if m is less than n, then we will add zeros to the smaller one. Or if m is greater than n, we'll add zeros to the second one, so they both have the same, right? All the higher order terms will add zeros, so they're both m. That way, the notation gets a little easier. But for example, here's a proof that vector addition of polynomials in the vector space P is commutative. And notice that as vectors, they are in bold. But when I prove the theorem, just like the scalar is the same lowercase letter with a subscript, we use the lowercase p for vector p, for little polynomial p of x with coefficients p naught to pm. And we use lowercase q of x for polynomial bold q. And we use its coefficients q naught to qm. Try to make it a little easier. But you see that the proof that vector addition of polynomials is commutative is not that bad. We have some ellipses in there and some dot, dot, dots in order to not have to write everything down. But, right, because m could be 5,280. But an associative looks a lot busier. But that's because we have p hat, p bar, q bar, and r bar, which are p of x, q of x, and r of x. But it's still associative. And it's associative because each one of those coefficients for the like ordered terms are just real numbers being added together, and that's associative. It's almost the same idea as why vector addition and matrix addition are associative. Yeah.
So I want to clarify about this. Are you representing the coefficients of each term of the polynomial as vectors here?
No.
The polynomial.
Each one of the coefficients is not in bold. At p naught to pm, right, are scalars. They're the scalar coefficients of something that's kind of abstract, which is the x to the 0 through the x to the m. See, vector p in bold is a vector in the vector space capital P of polynomials. But we can't write its column vector because we would need an infinite number of zeros after the mth one. Mth one. I didn't know I'd ever have to say that. Nth, I've said. Okay, so we write p of x. Not bold, normal font, little p of x is the same polynomial, but written using function notation, rather than bold p, which is the vector in the vector space.
So there's no abbreviation we can use this time?
Well, abbreviation.
Well, not abbreviation, special notation like we did with.
The problem here is m could be any finite number, right? Give me some time. I'll get us back to something that's a little easier to write down. Obviously, the vector that has zero slope and y-intercept 0 and the horizontal line as its graph is the 0 vector in this vector space. It's the polynomial 0 of x, which has as all of its coefficients zeros, or plus 0. It only has one coefficient, right? The constant coefficient, which is 0, followed by an infinite number of zeros. All right. If I add the 0 polynomial to any polynomial, I don't change it. I get the same polynomial. And polynomials have additive inverses in this vector space. After all, we just multiply all the coefficients by a -1. And now if we add that new polynomial to minus p of x to p of x, I get the 0 polynomial. Right? So I've just proved that p plus the minus of p in bold is equal to, in bold, the 0 vector in the vector space, capital P, of all polynomials. Does this make sense? You starting to see it? Now, okay, I stopped there at 5. There are 5 more, but I'm hoping that if you had an obviously there's an exercise in the homework, right? The other part about this chapter is it's the one that has the longest homework problems. right? Because it says, show this is a vector space. Oh my gosh, do I have to show all 10 of them? Yeah. Okay, so long homework problems. Okay. What are some other ones? This one you might like better. How about P sub n, the finite dimensional subspace of polynomials of degree less than n? Okay, your author makes what I think is a mistake, and I have seen this in other places. He defines Pn to be the polynomials of degree less than or equal to n. But that means that Pn is an n plus 1 dimensional vector space because you have a constant term. And I think that our n is an n-dimensional vector space and Pn is an n-dimensional vector space. It's just that we use coefficients P0 to Pn minus 1 for our coordinates because we have x to the 0, the constant term, and then so we're going to stop at x to the n minus 1 because elements of Pn should be a list of n numbers, right? You see why? So there are those of us who think that when you write m by n, that's m times n numbers. And when you write Rn, it's a list of n numbers. And you write Pn, it should be a list of n numbers. But a list of n numbers gives you a polynomial of degree n minus 1 because you have a constant term. So we're going to call the coordinates P0 to Pn minus 1, not P1 to Pn. Do you see why we start with 0 instead of 1? And we only do that for Pn because it makes sense, because those are the powers of x. Okay. Show that Pn, the set of polynomials of degree less than n. So in this class, unlike the textbook, it's less than n, is a vector space. Let's get started with that. Okay. If P and Q are vectors in Pn, that means they're polynomials P of x and Q of x. We figured that out in the last one, example. And we can write them this way. Only now instead of an m here, we have an n minus 1. Okay? But Pn, unlike P, is a finite dimensional vector space. We can represent that polynomial by a column vector that lists the coefficients from the constant term to the highest order term. Well, doesn't that mean that we could use the notation that we learned in the last chapter? In chapter 1? So now you're back to the nice notation.
Yay. I like that better.
Now, does this mean that Rn and Pn, which is why I say it's the polynomial's degree less than n, have some quality about them that's the same? Aren't they both described by a finite list of n things, n numbers?
Doesn't that make all polynomials an infinite dimensional vector space?
Since both of them can be, what?
Doesn't that make them both vector spaces then?
No, the fact that they're similar does not make them vector spaces. They are vector spaces that happen to be similar. I'm talking about Rn and Pn, finite dimensional vector spaces,
Okay.
right? So Rn is a vector space, we knew that already, and now we realize that Pn is a vector space, but they're both described by a list of n numbers. So from the computer science perspective, is there any difference?
No.
Okay, there is. One of them, the list of numbers represents an arrow in space, or it represents something else that requires a list of n numbers. In Pn, the n numbers represent the coefficients of a polynomial of degree less than n, right? But from the computer science perspective, it's a list of n numbers. This is why you're in this class. From the computer science perspective, we say, here's the vocabulary term, that Pn and Rn are isomorphic. I know that's a really, really $150 word, but that's the term that mathematicians came up long before any of us were born. They're called isomorphic. Isomorphic means iso, the same, morphic, shape, right? They're the same shape. Now, every finite dimensional vector space that requires a list of n numbers are isomorphic to each other, right? And from the computer science perspective, they are all just lists of n numbers. So your computer doesn't care what the list of n numbers represents, right? We apply meaning to the list of n numbers, but the computer has no meaning for them. But we now realize that the algebra is exactly the same for all lists of n numbers. So the algebra of polynomials of degree less than n, the algebra of vectors in Rn, the algebra of every finite dimensional vector space that has a list of n numbers that represent the vectors in the vector space are all isomorphic to each other, which means the computer can do the same computations in an eye blink, right? And we will apply meaning to it. Okay, and much of 21st century technology is built on this very fact. Okay? All right. And again, if we're going to be proving things about polynomials of degree less than n, obviously this is the way to go. This one is okay. That one's right out. All right, this is the most difficult. That's okay. This is obviously the way to do it. Now this one looks longer because it's property 3 instead of property 2, right? Property 2 is an easier one to prove than property 3 because it's property 2 you only need 2 vectors and you're doing commutative, and in property 3 you have 3 of them and you're doing associative. Now let's talk about a different vector space. All right. To a mathematician, a function is the same thing as a vector. How is that possible? Well, okay. A vector has, let's call a vector in R8, has 8 coordinates, right? Isn't that a function from the set of 8 numbers to the real numbers, in which a of 1 is its first coordinate, and a of 2 is its second coordinate, and a of 3 is its third coordinate, right? And a of 7 is its 7th coordinate, and a of 8 is its 8th coordinate. So a vector is a function. It just maps a finite number of numbers to the real line, to the real numbers, and it just picks 8 of them, right? Well, this is the function like y equal x squared. It's just that how many coordinates does it have? Does it have a coordinate for every number in the real line? So it has a lot of coordinates. But its y value would be the coordinate you get for that index. So we call the domain of a vector function the index of the function, right? Or the element. And we call the thing you get in the codomain, the real numbers, the coordinate. So we have index 1, 2, 3, 4, 5, 6, 7, 8, and 8 coordinates, 8 real numbers. And we list them because there are only 8. But we can't list every single x squared for all of the x's in the real line, because that would be a really long list. You understand? So instead, since the real line is a continuum, it's a line, we have the codomain for the real axis y, and we just draw the parabola. And if you want to know a coordinate, you pick an x, and you find y equal x squared. And that for that index x, you get its coordinate, y, equal to x squared. So it's the same thing. A domain, a codomain, and a rule for figuring out the element of the codomain from the element of the domain. You have an index, and you have real numbers, and you have some rule for figuring out the coordinate from the index. And usually that rule is written by listing all 8 of them. Right? When I write down a vector in R8, I'm writing down a function. It's just that there are only 8 numbers in the domain. So I can write the function by simply listing all 8 of the elements of the range, right? 1, -2, 3, 5, -7, 6, 12. I made the first ones too far apart, didn't I? 13, right? So if this is vector A, then A is a map from 1, 2, 3, 4, 5, 6, 7, 8 to the real numbers. that follows this rule. Okay. While my mouse and my tablet fight for dominance. Okay, when I have y equal x squared, you've been doing this sort of thing for a long time now. We have blurred the distinction between the name of the function and the name of the dependent variable. We just call it y. And you're supposed to infer the domain and the codomain.
Well, they're the same, aren't they?
In this particular case, but what if we had square root?
Then they would not be the same.
Yeah. All right, so in this particular case, y equals x squared is our rule. Why? Because we can't list the uncountably infinitely many number of real numbers and the value of x squared for every single one of the x's in the real line. That would be just too long a list, right? So instead, Descartes came up with the idea, which is why it's called the Cartesian plane, of drawing the domain and the codomain, and then just drawing a picture of the curve, y equal x squared. Okay, I'm not very good at drawing on this thing, right? And now we can see the coordinates for every single index x, right? And so we write, in fact, you started writing things like y of x equal x squared. And it is, in fact, possible to write a of I, but we usually write it this way.
Yeah.
But we mean a bar of I, if you're using the mathematician's perspective. So functions are vectors too. After all, isn't the sum of two functions a function? And if we multiply a function by a scalar, don't we get another function? And doesn't addition of functions removed from from algebra class, the algebra of adding and multiplying functions by scalars follows all 10 of those rules? Now, we're not so much interested in all possible functions on the real line. We're interested in a very special subset of them. For example, the continuous functions. After all, isn't the sum of two continuous functions continuous?
Yes.
We learned that in Calc 1. Since that was already learned in Calc 1 and it's a prerequisite, you can use that as a fact. You do not have to prove it. Okay? The sum of two continuous functions is continuous. Isn't a scalar multiple times a continuous function a continuous function?
Yes.
Isn't the zero function, you know, the function whose graph is the horizontal line with y-intercept 0 and slope 0? Isn't that a continuous function?
Technically, yes, it's a constant, so.
Aren't constant functions continuous functions? Aren't all constant functions continuous functions? Aren't all polynomials continuous functions?
Yes.
Yeah.
Whether or not the scalar you multiply it by, oh, actually, no, never mind.
Doesn't matter what scalar you multiply by, you get a continuous function.
Yeah. I think it's so different.
So the space of all continuous functions on the real line with our normal idea, I hate that it interprets that as changing. So Windows does this thing where if I can't see it, it interprets clicking on the scroll bar as changing to the app underneath. And I don't know when they started that, but they need to stop. Okay. Where are we? It's too bad I can't see the scroll bar. There we go. No, you see what I mean? If you look at the graphics here, that's the scroll bar. But if I tap it, it won't do anything. Now it's not doing nothing. Okay, finally. Oh, we're at the bottom of the page. Okay. Thank you. Let's get a new one. So, we write C for continuous functions on the whole real line, Or we can write continuous functions from minus infinity to plus infinity. Of course, we use round brackets because plus infinity and minus infinity aren't endpoints. They are, I don't know, ideas. Don't stop.
Their sizes.
This is a vector space. As long as we add our idea of addition of functions using, the algebra of functions, f plus g of x is f of x plus g of x, and scalar multiplication, then this is a vector space. Usually we don't write all that fancy stuff. We just write is a vector space. And if we limit the domain to some interval on the real line, which is really common, especially in engineering, then we get the vector space of continuous functions whose domain is the interval from A to B. If we use square brackets, you include the endpoints, and if we use round brackets, then you don't. Why do we almost always use square brackets?
Because we're dealing usually with round numbers.
No. What do we know about a continuous function on a closed bounded interval? It attains its maximum and minimum, right? Remember this from Calc 1? A continuous function on a closed bounded interval always attains its max and min. So continuous functions on the real line, like y equal x squared, it never attains its maximum, doesn't it? It just keeps getting bigger and bigger and bigger.
Well, of course, because there is no maximum.
Right, but it has a minimum.
Right.
But a continuous function on a closed bounded interval has a max and a min, and it attains it. There is a number between a and b, which might be a and b, or b, where the function is max or min. We can also talk about differentiable functions. When I put a 1 up here, I mean the function is differentiable and that derivative is a continuous function. So, this is the vector. After all, isn't the sum of two two differentiable functions differentiable? And isn't a scalar multiple times a differentiable function? Okay, so we have the vector space of all continuously differentiable functions on the real line. We say continuously differentiable because when we write C1, we want it to have a derivative, and we want that derivative to be continuous. And then the one that's the most important in differential equations, functions with two continuous derivatives. So it is two derivatives, so it's a solution to a second order differential equation, and that second derivative is a continuous function. So it's twice continuously differentiable. And these are the three vector spaces we're really interested in. These are the ones that we are using our 21st century technology of computers to solve problems with. Okay. And isn't the set of complex numbers a two-dimensional vector space? Right, the sum of two complex numbers is a complex number, and the scalar multiple, a real multiple of a complex number is a complex number. There's a 0 plus 0i. And so, but it takes a list of two numbers, right? An A and a B. So it's a two-dimensional vector space. Oh no. Does that mean that Cn, the vector space of the 2n-dimensional vector space of lists of n complex numbers, is a vector space? Yes, it does.
Wait, did you just say the vector space full of vector spaces?
This is a 2n-dimensional, in real numbers, but an n-dimensional complex valued vector space.
So
Is
would
it-
that imply that quaternions are also vector spaces?
Yep. And that means we can also have this vector space of m by n matrices of complex numbers.
why complex numbers are always so difficult to work with then. Because if you have two vector spaces, if you
Well-
basically have two vector spaces opposed to each other, it's like you're dealing with a function of x and y with.
You can think of it that way, or you can think of the complex number as a scalar. And so Cn is an n-dimensional vector space, but it is a 2n real dimensional vector space. C m by n also doubles if you think of each complex number as two real numbers. But if you think of each complex number as just a scalar, and you allow complex valued scalars, then it's an n-dimensional vector space and an m times n dimensional vector space. Yeah.
That makes sense. My point was that why complex numbers are such a bear to work with when combined with x and y notation is because you're basically combining one vector space into another.
Right, but
And it's that.
But if you lose that and you start thinking of complex numbers as a single scalar, you can take a class, complex analysis for engineers, and in fluid dynamics and quantum mechanics and electrical engineering, complex is used a lot. And the thing is, there are real advantages to complexifying the problem and thinking of the scalars in your problem as complex numbers instead of real numbers, right? In fact, there are some mathematical physicists and mathematicians that are trying to represent particle interactions in particle physics using octonions.
So we haven't used for a turian?
So, well, we might. Quaternions are used in robotics. It's time to go, so let's stop recording, but I can explain that unless you want me to explain it at the beginning of class next time. I can explain it in the beginning of class next time.